course. What are graphs? So graphs is an ordered pair of a set V of vertices and a set of edges E. What does that mean? Ordered pair means AB is not equals to BA. In terms of that, let's an unordered pair is uh, A A comma B, but all in one, all in that. So let's look at that. What does that mean? Let's start with this example. Yeah, we have the lines. We can call them the edges, and the corners we can call them as vertices. So imagine if it would be just a corner or a small dot, that will be considered as a vertices. So how many vertices we have? 1, 2, 3, 4, 5, 6, 7, and 8. And how many edges we have? If we count the lines, we'll know there are 10 lines, and all those lines are called edges. So this graph is a complete ordered pair set of vertices and edges, where AB is not equals to BA. You will be able to understand a little bit more when I will scroll down to the next few slides. But graph is the ordered pair of vertices. It's not an unordered pair, meaning that AB cannot be replaced by B, can be replaced by BA if it's an unordered pair. But in an ordered pair, the order does matter, and you cannot swap out AB with BA if A is not equals to B. That's a little bit of mathematical part, but let's look at it visually. So we can name each vertices as V1, V2, V3, V4, and all those are called vertices. If I am going to write that in an unordered pair, we can write it this way: V1, V2, V3. These can be changed. V2 can come first, V1 can come afterwards, V3 can come first, and V8 can come afterwards, or V8 can come first, because it's an unordered pair. All we are determining right now is how many vertices I have. But when we will talk about V and E together, it means we cannot interchange V1 E1 with V1 with the E2 E1 V1. We cannot change that way. So I repeat, we will have unordered pair list of vertices. That's fine. I'm not looking at this at the moment. We can have the vertices like this. We can have edges like these as well. If I name these lines as E1, E2, E3, E4, and all blah blah blah, continuing to 10 of those, so up until like E10, they will be individually unordered pair list. But when I talk about in combination of graph, graph is equals to V and E, then we will pick up V1 comma E1, meaning that what vertices this node, we call it node as well, the vertices can call also be node, what nodes this V1 is connected with. So obviously if I just for supposedly say this one is E1, this one is E2, and this one is E3, we cannot say V1 uh, V1 with E4. We cannot say that, or we cannot say, because V1 is not connected to with that, the combination will be wrong. Yes, we can say V1 with E1, V1 with E2, V1 with E3, or we can say V1 with E3, V1 with E2. That order can be changed, but we cannot say that V1 with E5, because the order will not, this node is not actually hitting that line anyway. So all those nodes that are hitting the lines or the edges, they are they are put together in the graph format like this. So if I have to type, yeah, there's a type of graph which is called directed graph and undirected graph. Easier concept. You can go from node U to node V, or node A to node B, or whatever the node is, in one direction. So it's a directed graph. You cannot come back from V to U unless you have another arrow showing up like that, or you don't have to mention the arrow if it's a bidirectional or undirected graph, meaning that you can go from Red Deer to Calgary and you can come back from Calgary to Red Deer as well. It's a undirected graph. But in a directed graph, it's a one-way graph going from U to V. We can convert this graph into bidirectional graph or undirected graph by putting up the arrow like that. But at the moment, if you look at this diagram, it is a directed graph only. So we can have two ordered pairs like this. If we are converting this into a directed graph, we have to make arrows and this arrow back, and we can now write UV to VU as well. That's fine. Let's say if you are taking highway 2 and not just taking highway 2 and going to Calgary from Red Deer, and then coming back in the same direction, coming from Calgary to Red Deer using the same highway. If it will be a different route that we have taken off, then this will not be a directed graph. So just think of that. So the implementations of the graph is not limited to what you are seeing right now on the screen. Google Maps is the biggest example of graphs. Right? You go from destination. So how they made this kind of, how they came up with this. Probably they have worked on this with the directional and undirectional graphs, like, right? So you have destination A to destination B, and then you can come back from destination B to destination A back again. So it's an undirected graph, or you can have a directed graph, but then you have to mention both the ordered pairs. And what does that mean? Ordered pair U to V and V to U is the second ordered pair. Usually, if we take the same route going from V1 to V2 and coming back from V2 to V1, that's an undirected graph, meaning that going from Red Deer to Calgary and coming back from Calgary to Red Deer, it's an undirected graph because we can go both ways. Undirected graph, as you see, is written in this format of brackets. But let's keep it back to what we were talking about, that what is directed graph. It's a unidirectional. So in the undirected graph, we can create all the edges, and we can find out what are all the edges, and then we can put them in any order. So first, start as a chronological order. We can start with V1 going to V2. So that's first unordered pair. This is a second unordered pair. So all the possible combination, V1 to V2, V1 to V3, V1 to V4. Then the next you move to the next node, V2 to V2 to V5. V1 to V2 is already done, so we are not going through that because it's a bidirectional graph. It's a undirected graph, so we don't need to write V2 to V1, but V2 can go to V5 and V2 can go to V6. Same thing with V3. V3 goes to V7. There is no other way it is going back to V1, so we are not writing that. We can have some part of the graph directed graph, and some part could be undirected. So but undirectional and ordered pair. So meaning that you can have some of them can have bidirectional attached to it, but most of the time what we will be studying is this graph, which is more versatile, because let's see what we are going to do, but just think of that in this graph. So not just the implementation of graph is not just limited to uh, not limited to bidirectional unordered pair. What else we can think of the graph? Let's say on the social media network like Facebook, you have immediate friends. So let's say if I pick up the example of Rama, and that is what is explained in this uh, example. Rama, I'll just see if I can, yeah. So there are some friends that are connected. So Rama is direct friend with Ela, Rama is direct friend with Katie, and Rama is direct friend with Bob. These are the three immediate friends that I'm seeing that Rama is. Now, if the question is asked sometimes, and you have seen in the Facebook, uh, sometimes it suggests you friends. How does it able to suggest some friends to you that you might have a friend? It's a sometimes a mutual friend, or sometimes like it does suggest you friends. How is it to go through that and make you those kind of suggestions? Because you are connected directly with these three guys. If it is asked to, if Facebook goes and asks you to, hey, I have some friend suggestions with you, for two possible reasons. It can say, find all the nodes having the length of the shortest path from Rama equal to 2. So all those nodes which which can become friend of Rama with the shortest distance of 2. For example, Rama is connected directly on social media with Ela, Bob, and Katie, which we already know. Now, if I'll say with the shortest path of 2, meaning that Rama, if I highlighted what are the two of those could be, meaning that if I'll say in the picture here, this is the shortest distance of 1, which is highlighted as yellow. What is at the shortest distance of 1 with the shortest distance equal to 1? If I change this question for a short period of time to 1, you can say that 1 meaning that Rama can have one friend Ela, one friend Katie, and one friend Bob with the shortest distance of 1 each. So if I'll put a weight here, this is a direct connection with the distance of 1. And that distance is not distance of measuring, it's a direct connection, I would say. Direct connection of 1. Direct connection of 1 with Bob, direct connection of 1 with this. It's a one-to-one relationship according to database. Now, what is the other friends that are Bob has? Bob has a friend Lee, Bob has a friend Tom, Bob has a friend Sam, then Katie has a friend Lee, and Katie has a friend Swati. So what are the friends that can be suggested to Rama? With the shortest distance of 2, if you see the items in the green, and if you read these questions, can you suggest some friends to Rama? Tom, Sam, Lee, and Swati. How is that possible? Rama is already friend with Ela, and the second shortest distance is Bob, so that could not be a friend. But Bob is already that could not be a friend because it's already a friend through Ela. And Rama is also directly connected with Bob as well. So if on the shortest distance, if I count this one, Rama can be a friend with Tom on the shortest distance of 2 from here. If I count 1 and 1 here, this 1 and 1 is already a friend, so we don't need to suggest that as a friend. It's already a friend. If I talk about this Bob, he can suggest Tom as a friend, and he can suggest through Bob, you can suggest Lee as a friend as well. Same with and with the Bob, we can suggest Sam as well. as a friend. So we have two suggestions, actually three suggestions can come out from through Bob: Tom, Sam, and Lee. With Ela, we could not suggest any further friends because Ela has only one friend, Bob, which is already a friend of Rama. The last part, if I contact one connection with Katie and second connection is Lee, on the shortest path of two, Lee can be suggested as a friend. So Rama could have a very likely to be a friend with Lee, but he has not added Lee, uh, as Bob could be a friend of Lee and Katie could know also a Lee, but Rama is not connected directly with Lee at the moment. One friend suggestion for Rama could be Lee for sure. Through Bob, we have Tom and Sam as a friend. This Sam is not coming through Katie or Ela because Katie does not know anything about Sam. And last thing, Swati can be a friend through Katie. So these are the four entitlements that you can see that can come as a friend to Rama. So I don't think so. The answer is Tom, Sam, Lee, and Swati. And based on what we just looked at that, find all the nodes having the length of the shortest path, and this is the answer. It's a little bit of inverted slide, but the other example is the World Wide Web. Pages pages on the internet are connected sometimes, but for example, let's look at that think of that. I'm thinking of a couple of examples here. Let's say I develop a web page. I develop a web page P, and on that web page, I provide a link of Wikipedia web page or a Wikipedia, or I provided a link for Google or provide a link for YouTube. It is not necessary. It is on my web page, and it's a directional graph that I'm calling it now. The example of this is World Wide Web. So on the page P, on my personal web page, which I just published, let's say today or yesterday, I put a link to YouTube or Wikipedia or Google or whatever website that I like, my favorite links or something like that. But as you can see, it's one directional, meaning that if you have put this web page link on your website, it is not necessary and it is not being seen that YouTube is entertaining and highlighting you, that you have put the page, that YouTube is not obligated to put the page, put your link on their web page. YouTube is not diligent enough, and YouTube is not publicizing you to say that, oh, there's a new website launched by Kashan, I want to propagate that. No, it's a unidirectional graph. You are just increasing the popularity, or you are just connected, that you are on your web page, you are linking people to go to that website, but that website is not obligated to put your web page link on that. If they are, there could be, if there is a friend's website, for example, something like that, if you think, hey Kashan, you developed the page Z and you put my link on your web page, in a friendship return, what I will do, on my web page I will put your link as well. This is a bidirectional graph, meaning that it's a kind of a tit for tat. If you are doing something in favor for someone, somebody is putting your web page on their link. So this can happen. So, but for the most part, 99% of the time, we see that They are not obligated to popularize you or do the marketing of your web page. Yes, you can put the link to that, or if you have a favorite YouTube video which you want to put the link on your web page, you are good. But now most of the time, this is the web, how it works. This is very uh, this is this is not the common practice that you see on the web, but it does happen. Sometimes you can think of it like that: if you subscribe my channel, I will subscribe your channel. That is one thing that you can do, but it is not like saying that if you are putting or you like my video, I will like your video. Yeah, that could be a another tag play game between the websites, or directed graph, bidirectional graph. So if I put that video, that's the same example, just like I mentioned on the YouTube or Wikipedia or something like that. So if I put that page, they are not obligated to that. Next thing is the weighted graph or unweighted graph. We can have the graph, bidirectional undirected graph between intercity links. If you look at that, there is no weight put onto those links. They are just city A connected with city B and C and D, or whatever the city is. It's an unweighted graph. It's the um, undirected graph connecting cities each other, just like I mentioned about city A and city B. Let's start putting some weights on those nodes. So let's say if I'm considering these as a kilometers, A and B are connected with each other at 150 kilometers each apart. B is connected with C 180 and so on and so forth. We have all those kilometers listed here. Again, this brings me an example of Google Maps in my mind all the time. It could be destination A to destination B. You don't necessarily need to consider cities. You are just thinking of coming to the college, going back your home, or going back to, or stop by for groceries in the middle or whatever. But that has a weight associated because you are associating kilometers with it. You can associate not just only kilometers, but you can associate the gas to it. So obviously, if you live further from the college, the more distance you have to cover. That's one weight. Second type of weight would be more gas you have to put in. That's a weight of, or that's a cost of uh, your gas money, right? There are so many different weights types that you can think of, you can attach, but I'm just thinking about two of them. So these are different weights that you can associate, not just kilometers. But in general, if you usually associate kilometers with the weight. So if I think of that, and I'm coming towards the end of this, but look at this, is that if I need to go from city A to city D, from the look of it, it always looked like that what will be the shortest path will be, oh, by the look of it, it looks like with the small connection between the arrows, or a small connection that we think, oh, this will be the shortest path. It's not, it's highly unlikely. If you sum up 150 plus 180 plus 150, I don't know how much is it, but if you go from these three different directions, I'm not sure, maybe I will see in the next slide, I'm not killing my eyes calculating this, what will be the shortest path. This is the looks like a shortest path, but it is highly unlikely. Maybe it could be that you create a bigger arrow or a bigger distance, and you find out later that the weightage is much smaller. So let's say if I make this only a 50, this 600 is not 600. If I make it a 50, then you can think of that from the looks of it, the join looks very smaller. and that we assume sometimes that that will be the shortest path. But if I'll just say 200 plus 50, that will be only 250, and then you can reach from city A to city D in a very efficient way of kilometers and gas as well. But if you look at this way at the moment from the slide, I can guarantee that looks like this one is the shortest path, 150 plus 180 plus 150. But that's not the case all the time. You can have multiple different routes to go to a different city.